Hi everyone and welcome to Lab 8. So I am in our Blackboard site now like normal in our week 13 file within there, the Lab 8 folder. And so I'm just going to download all of the files that come with Lab 8 in the archive.zip like normal. I'm going to open up downloads and it's going to automatically sort of extract everything. Now let me show you what's in there. We can see the R script, we can see happiness data, and we can see the PDF that goes with this. So in our case, the PDF is about 5 pages long this week. So like a reasonable size. And we're going to be going over regression diagnostics. So let's open up this R script. So let me close some of these things down. Don't save. As you can see, I keep a lot of things open all at once. It's a terrible habit. So let's clear everything from my global environment. You can see that I have lots of things going on there. Command Enter. I need to set my working directory, choose directory, to my downloads, which is where I have the data unzipped right now. Just not really a good data practice to just keep it in downloads. But for these purposes, we will. And we're going to load in our data set called happiness data. So let me just run you through real quick what that data set is. This is every state in the United States, they got an aggregate happiness measure or score. It ranges from 0 to 100, with 0 being unhappy and 100 being happy. Income here, this column is the median household income. I expect that income will have a positive relationship with happiness. I also have the unemployment rate. I expect in that case that it will have a negative relationship. So as unemployment increases, a state's unemployment increases, that state's aggregate happiness score will decrease. I also have here education. This is the percentage of people with a bachelor's degree in the state. Here I expect that as the percentage of people with a bachelor's degree increases, that happiness will also increase. I've also included park acres. This is literally the number of both state and national parks in each state, with the idea being perhaps that the greater access to parks, happiness will increase in the state. So access to green space in studies of cities is often associated with increased or improved well-being. This here is a cost of living index. That's what COLI stands for, with higher numbers being associated with higher costs of living. So you can see here that Alaska has a cost of living index of 130.6. That is, it's very expensive to live in Alaska. It makes sense, especially given the transportation and food costs. Here we have Arkansas. It has an 88.4, so it's much cheaper to live in, say, Arkansas or Oklahoma. So just to get back to our script, in order to, if you'll recall from Lab 1, R is just sort of like a basic calculator, and sometimes we need it to do slightly fancier things. In our case, we're going to be using a couple of packages called MASS, M-A-S-S, and CAR, C-A-R, to do something a bit fancier, specifically using it for outlier diagnostics, so identifying which states are potential outliers in our models. So in this case, I install them, install.packages, install.packages car. So this installs both of the packages. That doesn't mean that the functions that we need them for are active just yet. This is why we do library mass and library car. So in these cases, lines 7 and 8 install the packages, including their commands. But in order to make those commands active, I need to use the library. Now, in the cases of packages, you'll only ever need to install them once. So unless you're using another computer, something like that, you should only have to use install.packages once on your computer and once in your R session. It will be in your version of R until you update R or change computers. But if you want those commands active for the session that you're in, you do need to use library. So library mass and library car. If you need a little bit of sort of refreshing on this concept, I would encourage you guys to revisit Lab 1 or even look over the associated PDF that comes with this document, because there's a little bit more detail in there. So let's look at nonlinear relationships. So as I briefly mentioned, I expect that as median household income in a state increases, happiness will also increase. So I'm just using regular language here, right? Happiness is my dependent variable, tilde, and then income. So let's run it and see what we get. As you can see here, income has a positive, right? See how this coefficient is positive, and statistically significant relationship with happiness, given that this p-value here is much less than 0.005. So therefore we can conclude that income has a positive and statistically significant effect on happiness. But what if either by looking at previous literature or my theory, or even if I look at a plot of the observations looking at the relationship between income and happiness in my data set, I instead come to the conclusion that income has an effect on happiness, a positive effect on happiness up until a certain point. And then beyond that, it's positive effect ends up declining. So it either plateaus or maybe it even starts declining. In that case, I would want to include a squared term. I would want to include a quadratic term, is what we tend to call them. So in this case, I'm going to make a new variable called income squared. So this first part here says, I want to make a new variable in the data set called data, and I want to call that variable income squared. And this variable will be composed of income, our variable income, squared. And you see this little hat here, this little carrot top right here, and then a 2. That means square the values in this variable. So I'm going to run that and I'll show you what it looks like in the data set. So I'm just going to open up, click on my grid and look at the data set. And if I scroll all the way to the right, you can see here now my new variable income squared, which is just this variable income times itself. So this number here, 188,955,3961, is just 43,469 squared, right? And we do that for each of the states. So then I'm going to put both income, the original variable, and income squared together. They have to be included together, okay? And I've called this new model mod 1 squared. So let's see what this model looks like. And we'll try to determine which one is better. So in our case, we see that income, the original variable, has a positive effect, and then income squared has a negative effect, which is what we would expect. We would expect that as income increases, there will be a positive effect on happiness, but there are likely diminishing returns beyond a certain point, which is why we get this negative here. So let's look at model fit, right? Let's look at the R squared. So with the squared term in the model, we have, it looks like 51.8% of the variance in the dependent variable, happiness, is explained by income and income squared. Now let's go up to our original model that just had income. In our case, it looks like income only explained 42.14% of the variance in our dependent variable happiness. This leads me to believe that including both income and income squared in our model improves model fit and better explains the data generating process. It better explains the relationship between income and happiness. All right. So how would I interpret this? How would I interpret these coefficients? Much like interactions, you cannot directly interpret these coefficients. You cannot directly interpret these coefficients. But again, just like interactions, I would encourage you guys to plug numbers in. So let me just type out what the equation would look like. So I'm just copying and pasting the coefficients in right now. So let's say that one person, we'll start with our first estimate of $45,000. Let's see how much $45,000 squared. I'll put this in parentheses. So this is our intercept, right? This is our coefficient on income, and this is our coefficient on income squared. So we'll do intercept plus the coefficient times 45,000. This is sort of lower on our range of median household income by state, plus the coefficient on income squared times 45,000 squared. So you have to make sure when you put it in, 45,000 for the income coefficient, and then 45,000 squared for plugging in numbers for the income squared coefficient. So let's see what we get. So it looks like the average happiness score predicted by our model for a state that makes has a median household income of about $45,000, they would have an average happiness score of about 38.9. So let's up this income by 15,000, bringing us to $60,000. Let's see what point estimate we would get. So coming up to a median household income of $60,000, we see happiness scores increase by about 15 points, right? 16 points. So increasing income from 45,000 to 60,000 increased that state's happiness score by about 16 points. Now let's look if we bring this up to 75,000, which is closer to the high end of our scale in terms of median household income. Let's see what we get. So that only increases our happiness score by about 4 points, right? So increasing it 15,000 from 45,000 to 60,000 increased happiness scores by about 16 points. But increasing it again 15,000 from 60,000 to 75,000 only increased happiness by about 4 points, right? This lends evidence to our argument that beyond a certain point, increasing income does not necessarily translate into higher happiness levels. So the next thing that we're going to be assessing is collinearity. So here I'm going to just put all of my variables that I've brought in into our model. I'm going to include income squared, because I've just shown that income squared does matter. It does better fit our model. The unemployment rate, education, park acres, and cost of living. So I'm calling this mod 2, and I'm going to summarize mod 2. So here we can see that income has a statistically significant effect, as does income squared, but nothing else really gets to statistical significance, although I will say it appears as if Park Acres got somewhat close. Park Acres has a p-value of 0.13687, and unemployment has a p-value of 0.08445. So let's see, though, if there's any collinearity or multicollinearity among our variables that's potentially problematic. So in order to assess collinearity, we run a command called VIF. So you see this here on line 27, VIF, and then open parentheses and then include the model name. So VIF stands for variance inflation factor. We are looking for variance inflation factors for our independent variables that are above 5. If this output returns numbers above 5, then we could potentially be concerned about that. So let's see what we have. So we see that income and income squared have VIF values that are way, way above 5. Unemployment, education, Park Acres, and cost of living index are all below 5, so I'm not really too worried about those. But here we see that the income and income squared ones are quite high. But if you'll recall from lecture, there are certain circumstances in which we are not concerned about variance inflation factors. One of those is when we have included interactions or quadratic terms. In the case of income and income squared, of course these are highly correlated with each other. Of course they are very collinear. So in that case, these are ultimately going to have really high values, right? These are ultimately going to have really high values because income really was multiplied by itself to make income squared, right? Income was just multiplied by itself to make income squared. And so as a result, these are going to be highly correlated. And in that case, we do not need to be super concerned. The other circumstance in which we're not super concerned is when they are control variables. Typically, we're not interested in if there's multicollinearity in our control variables. The other, though, is if we are seeing collinearity, multicollinearity among our variables of theoretical interest, we sometimes do drop those variables and see which one best fits the model looking at our R-squared. So pretending that these are not products of one another, what we would do is we would drop income and run the model again without income, see what the R-squared is, run the model without income squared, see what the R-squared is, and then run it with both. Right, what we just did, and see which one best explains the data looking at the R-squared, right? Paying attention to that R-squared. How is the R-squared affected when we experiment with dropping these variables, okay? So the final thing that we're going to be going over is outliers. So how do we identify outliers? So if you'll recall from the beginning of this lab, we loaded in both the CAR package and the MASS package, which helps us use both the outlier test and QQ plots. So the outlier test, I'm just going to run it for mod 2. It's going to identify our most extreme observation from the model that we just ran, mod 2, right? The one that might be considered an outlier. So here it says to look at, well, that's curious. For here, it says to look at observation 45. In the previous iteration, it said 12, but we'll see which one is 45 on here. 45. Yes, okay, it's the same. So 45 is Idaho. 45 is Idaho. And it's saying Idaho is a potentially extreme observation. So we look here at this Bonferroni p-value right here at the end. If this p-value is above 0.05, so different than normal, if this p-value is above 0.05, then we can conclude that this observation 45, is an outlier, right? We can conclude that it is an outlier. So in our case, Idaho is a potentially extreme observation. Going to, if you'll see the output here, it said observation 45, and then in our data set, going to observation 45, it is Idaho. So what is so unusual about Idaho? Idaho has really high happiness scores, but very low income. Very low levels of both income and education, things that we would probably think would have a positive effect on happiness, and it bears out in other data as well. Here is another way to determine which ones are outliers. It is called QQ plot. So all you do with QQ plot is literally the command QQ plot, open parentheses, then your model name, and then I call the plot main equals QQ plot. But in our case, we could have called it anything. We could have called it outlier test. We could have called it lab 8 outliers. Let's try that. Lab 8 outliers. QQ plot. So, and it should appear in this panel here, in your plots panel. So make sure that plots is selected. So let's zoom in and take a look at it. So what it's showing here is that observations 4 and observations 45 are extreme. The QQ plot is going to identify by numbering the observations that are potential outliers. So we've already identified Idaho and how it's extreme, but let's look at number 4. Which one is number 4? It is Alaska. Looks to be Alaska. Alaska in our case has really low happiness scores, but fairly high income, right? So it's essentially the inverse of Idaho, but still runs counter to expectations. It has very low happiness scores, but really high income. So thinking about both Idaho and Alaska, what are some potential reasons that that might explain why Alaska and Idaho are behaving this way? In the case of Alaska, I might argue something like their unusual weather patterns lend themselves to lower levels of happiness. For instance, there are extreme amounts of both sunlight and nighttime at certain times of the year. And as a consequence, that may lead to lower levels of happiness. So something I could include might be a variable about weather conditions, right? To help explain why Alaska has such an extreme observation, an outlier, if you will. In the case of Idaho, I'll leave you to posit why. Perhaps Idaho has higher social capital, and that's something also that I did not include in this model. So in the future, I may consider adding that in to try to explain why Idaho and Alaska don't sort of fit this model, right? How they're outliers, right? So in our case, let's say we do not come up with explanations for why Idaho and Alaska behave so differently, why they're outliers. Instead, we may consider dropping the observations. So I will say my personal preference and what I do if I identify some outliers, I'll run the model with the outliers included, and then I'll run the model without the outliers included. And I'll see if the results change substantially. So I'm not really entirely sure what happened here, but in my data set that I had been using, Idaho and Alaska were the 2nd and 12th observations. But as you can see here in the output here, it's showing up as the 4th and 45th observation. So I'll need to just change that real quick. 4th and 45th observations. In our case, if I run mod 3, I want to tell it to drop the 4th and 45th observations. So this here, do you remember how we subset data last week in brackets? This here is saying I want you to drop the 4th and the 45th observations from this analysis with this little minus sign. This minus sign says exclude. And then C means it stands for C bind. So these two observations together. If there were more, I could put them in here. I could say 10, 12, 13, right, on and on and on. But in our case, we're just going to drop the 4th and the 45th observations. So, and we're going to call this model mod 3. So let's see how that went. So if you'll recall from our previous analyses, income and income squared were statistically significant. And they pretty much are still. But nothing else was, although in many cases others did approach it. The cost of living index is still insignificant. But park acres, which wasn't significant before, is significant now. Education and unemployment are getting close, right? You see they have p-values both of 0.07, but still they still don't quite meet that 0.05 threshold. So in the case of income and income squared, we see that the results here remain largely the same, but park acres is now statistically significant. So we might want to address that in a discussion. This is partially attributable to the fact that Alaska has a significant portion of park acres anyways, and it might be affecting the results here, especially given that they have so many acres but have really low happiness levels. But yes, these are some of the tools that you can use for both identifying outliers, identifying multicollinearity in your model, and also nonlinearity, and finally how to solve some of these problems. But if you guys have any questions, please don't hesitate to reach out.